Okay, I realize due to the timing issue, this being at the end of the class, we didn't really get to go over it that carefully. So I'm going to take some time to look at the results and hopefully clarify some questions. Okay, so here's the plane. And you were told to find 3 points, P, Q, and R, that are on this plane. So here's P, Q, and R. Most of you simply pick the intercept. So for example, 0, 0, -1 is for P. You could also do 0, -2, 0. And then this very last one, not very clean, but it would be 3 halves, 0, 0. Okay, so those are the 3 points on the plane. The next part of the question asked you to find PQ and PR. So PQ and PR. So this vector here, PQ, you can figure that out pretty easily. And you have this vector here, PR. And most of you were able to figure that out pretty easily as well. Okay, next you were told to cross the two. So we know that the cross product will give us this vector. I'm going to call it n for normal vector because we know that's actually perpendicular or orthogonal to the plane. Okay, so here's the setup. And if we go ahead and do the cross product, okay, and what you end up with is the I hat is -2. I hat, the j hat is +3 halves j hat, and the k minus 3 gives you +3 k hat. Okay, and so the purpose of the exercise was actually to recognize that these numbers here, -2, 3 halves, and 3, are just scaled versions of this. Okay, and so the idea being that the normal vector actually turns into the coefficient, or is a scaled version of the coefficients of the equation of the plane. So let's ask the question a little bit backwards. Let's reverse what we know. So let's say I told you that I know the normal vector is -2, 3 halves, and 3. And I tell you that one of the points on the plane is, let's just go with point P, okay, which is 0, 0, -1. Could you then write the equation of the plane? Yes. And the reason why that works is you can write the equation of this vector, okay? So what is this point here? Well, this point is just some random xyz, okay? So let's call it, let's give it a letter. Let's use S, okay? So then the vector SP, if you think about it, it really just looks like this, 0 minus x, or actually let's do PS. Okay, so PS is going to be x minus 0, y minus 0, and z minus 1, minus -1, so +1. Right, so we know if I dot PS with the normal vector, then that should equal 0. Okay, so let's see what this looks like. So if I dot PS with the normal vector, I'm going to get -2 times x minus 0 plus 3 halves times y minus 0 plus 3 times z plus 1, and that has to equal 0. Okay, so if we did this correctly, we should get back the equation of the plane that we had previously. So you can see it's starting to take form here. It's not quite what we have up top in the original problem, but if you multiply everything through by -2, which just scales it but doesn't change the plane, you get 4x minus 3y minus 6z, and if I'll move that over. Actually, sorry, I jumped the gun here. This is 3. And then if I move it over, that's going to equal 6. Okay, so just as advertised. So that's exactly what problem 10 is asking me to do. So if I have a plane and I know the normal vector, right, which is given here as 2, 3, -1, and I know a point, right, so the point is 3, 2, 2. And here's another point on the plane. So this is x, y, z, just some random point that's on the plane. I can write this vector, which is x minus 3, y minus 2, z minus 2. If I take that vector and I dot it with the normal vector, set it equal to 0, that will give me the equation of the plane that contains the point and has that normal vector.